So today's talk will be like numerical simulation, flow field, and thin film deposition of the plasma-enhanced chemical vapor deposition reactor. So we will talk in this presentation. We will go through these outlines, introduction, and overview for the general process of the reactor, PECFD reactor process. And we will focus on the shower head, which is our target in this study. And the motivation and objectives lead us to do this work. And then we will go for the modeling and the results and finally the conclusions. So any PECFD reactor consists of a shower head, which is our target. We can see here the shower head. So here you can notice like we have two electrodes, like the shower head considered the upper electrode and the down electrode used for supporting the wafer or substrate, used for which is like used for the deposition, the target. So target to deposit the material, a thin film over this substrate, this film. And we have these two electrodes, and because our reactor is a plasma-enhanced reactor, this is the reaction is happening. If we speak about the flow, we have inlet flow and outlet flow for the gaseous flow, use it for this deposition. So and also, so our study will be focused in the flow field for this reactor, mainly focus about the shower head. So as you can see, this is a practical image for the reactor, and here is the shower head. There is many types of shower head, and we will go through some of them. So this shower head could have many types. So the first one is a planar multi-hole shower head, and also you can have a shower head with a gas distribution, which is like basically there is like a gap between the inlet, and then you distribute over these holes. And then you can have, in this gap, you can add a porous material to enhance the flow. The function of the shower head, basic function, to provide a uniformity, deposition, thin film deposit over the substrate of the wafer, and to prevent non-uniformity. Also to distribute, to give a good even distribution for the reactants over the substrate. Also, it's used as a physical barrier support between the plasma and the down reactor electrode. There is some feature you have to keep in your mind when you design, when you choose a shower head or you design it for your purpose. So first of all, you have to look at the geometry, which is what we have done in this study. So you have to look at the geometry and how this geometry can affect the deposition rate. This geometry should achieve a uniform gas distribution and deposit a good deposit rate. The number also and the size of these holes, distance between the shower head and the substrate or the reactor gap. The shape also and the size of the shower head and the shower head nozzles. Also, one of the considerations you have to keep in your mind, the gas distribution uniformity over the substrate, as well as the material selection and the maintenance of the cleaning, because it will be it will have like fouling these shower heads, so you have to keep in your mind the maintenance and cleaning of these. The motivation which lead us to do this study to overcome the challenge and in the modeling of the growth, the film growth over the substrate, as well as we wanted to optimize the operation and search for the geometrical parameter which affect the reaction process. We also focused in this study about the thin film deposition rate, which is like we use it as a target, as an indicator for our study to see if the performance is better or less. So we use the deposition rate, the deposition rate. because this is the target to have in mass production. You have to have a high deposition rate, and even also for the distribution. Yeah, if you want a uniform distribution, you have this deposition rate should be uniform over all the substrate. So to do this motivation, we make some aims to create a 2D model for the PCFD reactor and the geometry, and to capture all the chemical reaction and the transport phenomena as well, and develop and investigate the strategy for designing this reactor. And we have done the CFD model for this purpose. The boundary condition for our CFD model were, as you can see in this graph, so this is the basic. We have done many geometrical studies, but this is the basic one. It's an axisymmetry model. Here you can see the inlet, and this is the gas outlet, and here is the shower head. The shower head will be different based on the cases we will study, and this is the reaction zone, which we will call it electrode spacing or the gap. And here is the target. This is which is the thin film deposit area, or the substrate or the wafer. Our model was an 2D axisymmetry with the length of the reactor is 10 centimeter and the outlet port is like 2 centimeter and the electrode spacing 3 centimeter. We have done an optimization for this electrode spacing, and we will see this coming. And here you can find the model parameters, the operating temperature and pressure, and the governing equation. We solved the basic conservation of mass and continuity and energy and species and so on. So the model building sequence was like starting with defining the geometry and then creating the mesh, which is like it's quite challenging task to do, and then solving. We used an ANSYS Fluent software to do this solving process, and then just do a post-processing to get some results. So the case study we handled in this study, we have 4 basic cases. The case number 1 is, which is the one we explained later. So the function of this case is to study the case 1 and case 2 function to study the directions or the port outlet location and direction to see these effects. And this is the case 3 and 4. It's different design of the nozzle inside the shower head, and we have 2 different designs. One is the basic design, and the other one with little neck over this, and it's also mentioned in the previous works. And here you can see for this first study, we just handle the nozzles as it is, just a simple holes without considering the nozzle to just see the effect. So we keep the nozzle as just a simple holes. And the reaction mechanism and the boundary condition we use in this study, we solve the ionization reaction and volume reaction. And the overall surface reaction is target, as you can see, because we deposit the silicon. So, and here is the boundary condition for this study. And let's go through the results and discussion. So the first study was to study the effect of the outlet port location, case 1 and case 2, on the deposition rate. So as we established in the beginning that this is the criteria for judgment performance. And here in the graph, we can see the deposition rate, the surface deposition rate, and here is the distance, which is present the wafer or substrate, starting from the center up to the outlet. Here you will see that case 1 is which is like the downward outlet. It's not showing, but this is the case 1. It's the downward outlet port is giving a much better performance than the sideward outlet. To see why is this happening, we have to go through the flow characteristics and to see the velocity distribution in the 2 cases, and then also the the gas, the inlet gas, saline gas distribution inside the reactor, which is basically give the position fit. So in this case, this is the case one, which is like which will like have better deposition rate because the gas distribution of the saline is here. And then the second study we have done, optimizing or searching for the best gap or the chamber height or the electrode gaps. We have done these starting from 1 centimeter gap up to 4 centimeter gap. We can see that as the gap of the chamber height is increased, the deposition rate also increased. But meanwhile, the uniformity, and defined in this equation, which is like the number of deposits. So you can see that if the gap is increased, the uniformity decreased. So we choose this is used to be the best point for analysis, which is like we explained. This is why we choose 3 centimeters. And then we kept all the other parameters, geometrical parameter and operational parameter are same, and we study 2 cases. We see the case 3 and case 4 for 2 different designs, the nozzle design, and we can see that the case number 3 is giving a higher performance in the deposition rate, high deposition rate than the lower case, than the other design. And then we choose this nozzle to be also our target nozzle, and then we go further to do analysis for this particular nozzle and study the effect of the angle, the outlet angle of this nozzle. And we use the base case, and then we choose a small obtuse angle and acute angle, and we see that you can see here that the obtuse angle is giving better performance with like the acute angle is decreasing 6%, and the obtuse angle is enhancing by 4%. So the conclusion of this study that we have done a CFD analysis for the shower head design, showing that these geometrical parameters affecting and can be enhanced if it's well chosen for the performance. We also recommend that the outlet port location should be downward to get a better performance. The chamber height should be carefully selected, and in this design we choose it to be 3 centimeters. Also, we can say that using shower head nozzle with an obtuse angle can increase the deposition rate and uniformity. We also recommend this finding to be useful for whatever who's using the shower head design. And thank you everyone for listening.
Thank you very much. Any questions from the floor? We have enough time, so I have one question.
Yes, Professor.
Short question. Basically, you have a simulation using safety tools.
Yes.
For the reactor.
Yes.
PCBD. Basically, purpose of the simulation is to know the deposition rate and also the uniformity.
Exactly.
How did you measure the uniformity from your simulation?
Yeah, we measure the uniformity through measuring the deposition thickness, the deposit thickness, and the deposit thickness is distributed over the substrate is different. So we take the maximum one and the minimum one, and we take the average.
And could you show me any figure about that?
Just if we go back to, here is the equation I use. So the uniformity is the thickness, the maximum thickness minus the minimum thickness over the average, and 1 minus to just give it.
So depending on the location of the atom, which area have a thicker layer deposited than any other place?
The center one.
Oh, can you show me the figure? Here.
Oh, yeah. moreover distributed all over the substrate itself and the web.
Okay. With that graph, the previous graph that you showed us,
Yeah.
uniformity and yeah. So the uniformity should be high enough, and also your definition rate to be higher enough. That's your objective.
My objective is,
Both of them.
yeah, the objective is to get
Nationalization.
the best deposition rate with the best uniformity.
Okay. Alright.
Actually, to add more, the uniformity is number one target. Deposition rate is a target can be considered in the mass production if you're concerning about timing of this
Oh.
deposition.
Oh, you have
But they are in somehow connected. The uniformity and deposition are connected. So, but the number one target is uniformity.
Oh yeah, yeah.
And this is
Definition
the
rate, you can have more time. Right?
Exactly. This is the practical problem they have in the industry. They have like non-uniform deposit thickness
Right,
over
right,
the
right.
substrate.
Yeah, yeah. And you have you compared any experimental result?
No. Actually, this is the future working. We also cooperate with some industry, so we send this data. But also the next step is doing the 3D analysis and send this result for the company to compare them with them.
What about the nozzle? You have nozzle, just a hole and two different types of nozzle you use.
Actually, doing the whole was just just for the case of study. It was not the target. It's not an actual one. The actual design we are doing is an actual particular nozzle with a complex design. But we done this simple one, just take it as a one punched hole, just to perform this analysis. But the nozzle itself, it has a complex design.
Nozzle itself enhance
Indeed.
functionality.
Yes, and this is why in this study we use two different nozzles, and in this study also we choose one particular nozzle and we study the angle of this nozzle. How is the angle? This also can affect. Is it has a relationship with the deposition rate or has no effect? And then we find it has effect, and we study this.
Have you compare the uniformity also depending on the nozzle type? Because you said uniformity is important.
Yes, but actually we because this came from a paper, so we just have limited number of figures, but we can do it. Yeah.
Any other questions? Okay, thank you very much.
Thank you.